3, 2, 1. Woo! Hello everyone, let's do today's challenge. Maximum score of a good subarray. I will say this is DP right now before I even read the problem. Because yesterday was DP, today most likely is DP too. Alright, you're given an array of integers and an integer k. The score of a subarray is defined as the minimum of everybody in it times j minus I plus 1. That's the total number in it. A good subarray is a subarray where I smaller than equal to k, smaller equal to j. Return the maximum possible score of a good subarray, which means 3 is the maximum wait, hold a second. I smaller equal to k, smaller equal to j. So I has to be to the left of k. J has to be to the right of k, inclusive. And then the score is the minimum of everybody times the count. And we want to find the maximum possible such score. How did I even come up with these problems in the first place? All right, so what do we have in our very first example? 1, 4, 3, 7, 4, 5, right? 0, 1, 2, 3. So this is the stuff. And we have to say I must take 1 from here, J must take 1 from here, right? And then we want to find the minimum. A minimum. So did I smell a dude, what I was trying to say? Segment tree? Did I smell segment tree? No, I don't want to do segment tree. I always hate segment tree because it's too difficult to set it up. I mean, with segment tree, you know the range, you know the minimum of the range. Yeah, you're given a range, you know the minimum. And then, but still, like, even if you know segment tree, that's probably still not right. Yeah, let's not segment tree first. Let's just try to see. Now we want to find a maximum, right? The maximum value. 1 take from here and 1 take from here. The minimum. What do you think? What do I think? Well, if I put J, let's say J is here, okay, and I can be here, 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 all the way to this. So if I know the smallest value, right, smallest value starting from here to here to here to here, I know the smallest value all the way through. If I do that, if I know the smallest, then I add a new one. That's or like all the way to here is a 1. All the way to here is 3. All the way to here is 3. All the way to here is 7. Okay, so that's the smallest value. And then what we want is the count, right? The count. The count from here, the count is 1 for J, right? No. Count is, count can increase, right? Count, every time you go far, count can increase. Count can increase. So I'm right here, right? These are the smallest value. And then I also know the count. I do know the count. So j is here, and I want to say, okay, what is the maximum up into j? Well, the maximum up into j, which means we need to include j, right? We need to include j, and then j we have a 4. The maximum. And we have, we have to go through everything. That's not right. Yeah, count-wise is counted 1. Now it has to be k. So this is the first one. So count will be 2, 3, 4, 5. Right? In this case, maximum was taken as here, 12. Or if I know the previous position, can I know the current one? If I know the previous position, I have, a range, and say the smallest in there multiplied by that is the smallest. Now for me, I got a new one. Okay, I got a new one. If the new one is bigger than the previous one, right? If it's bigger than the previous one, then the smallest value will remain the same, right? Or if you say I can find a bigger smallest value, right? If I can find a bigger smallest value, would that be possible? Because your count is bigger. Right, yeah, if it's a bigger smallest value, it's actually possible, right? A bigger smallest value. So because the previous, we might have a bigger one, but the count is too small. But now the count is bigger, so I can take that. So, nah, that doesn't feel right. I am at a position if I know the biggest, which is your count. Count. I mean, the max count is always going to be the size of the array, right? That will be the max count. And then the question is where the small value are. If I have, because this is here, right? If I say I will include a maximum is 1, 2, 3, 4, 5, 6, right? 6. And in this range, the smallest is 1. Okay? And the second smallest is this 3. And what range, what maximum range can you fit? Can you make 3 the largest value? Right? Because if you include everything, you have the maximum range. So then you have the minimum value. You can find that minimum value. And that will be your result. And then you say, okay, what's the next best one? Is when we find a bigger, right? Because we increase the minimum value. And when you increase the minimum value, inevitably, you will decrease the size. But we can see if this is a good bargain. So in this case, if I say I want a bigger, I want to exclude the minimum value. And what we find out is to exclude the big minimum value, all we need to do is just remove it. Then we have this. Right? Then we have this. This is 1, 2, 3, 4, 5. 5. 3 times 5, 15. Right? The next one is excluded 3 because anchor point is here. So it's on the left hand side. So we have to do this. Now the minimum value is only on this side, right? It's on this side. And I mean, we can do on this side will be this. So it's 4. So 3, 4, that's 12. And then we say we can exclude this. Then we do this, it'll be 7. So can we do something like this, right? We produce an array starting from the anchor point, going left and right, find the minimum value, okay? Then we start from the smallest. Because this one is always going down, right? This one always going down. So we find the smallest to include the smallest. Okay, well, the starter will always be the entire array, right? If we start from the entire array, and then we know where the smallest is, and we get a value, which is 6, right? 1, 2, 3, 4, 5, 6. Then we say we're going to move towards the center, right? So we have a pointer on both sides. And because the way we set up the array, it's going to decreasing on this side, decreasing on this side. So on either end is going to be the smallest. Then what do? Is we find which one is the smallest, and this one has to move until the smallest is completely gone. So I will become here. Then we pick the smaller between these two. That's 3. Total count 15. Done. Smallest move to here. Between these two, 4. 4, 12. Move. I think this is the way. Let's go 5, 5, 4, 5, 4, 1, 1, 1. Anchor point is 0. So this is the anchor point. So there's nothing on the left hand side. So that's just going to be 5, 5, 4, 4, 4, 1, 1, 1. We're going to do the same. I is here, J is here. Okay, the starting point, we have the whole thing with 1. So 1, 2, 3, 4, 5, 6, 7, 8. Answer is 8. And then we pick this one, right? This is the side. So J is going to move, right? J is going to move to here. So 4, so 1, 2, 3, 4, 5. 5 times 4 is 20. And this one move here. That's one 5, right? Then 5 times 2 is 10. So answer 20. Answer 20. All right. So I think this is the method. But now the question is, how do we implement it? We can build this. Easy. We can set up the K. Easy. And then we can have I and J. That's fine. And we'll say one side and we'll move. Okay. Let's give this a shot. Let's give this a shot. No, that's not the one. That's my Spanish. IntelliJ is the one. Okay, so I don't want to change the original one. So what we're gonna do is we'll do another array. Let's call it mins. Okay, new int nums.length, and we'll start from k. We say mins k equals nums k for int I equal to k minus 1, I large equal to 0, I minus minus. We can say mins I shall equal to math dot min nums I and mins I plus 1. So it's a prefix. Now this is a suffix, right? The suffix min. Suffix min. Every one we compare the current one and the one in there. Whichever is smaller. So we set it up. So it'll be 7, 3, 3, and 1, right? And then the same thing we can say int j equal to k plus 1. J smaller than nums.length. J plus plus means j equal to math dot main nums j means j minus 1. Okay, so this we built the mins array. Now what we're gonna do is we'll hit a pause. Return your pants. They're so I think I have a good method for this problem. And it's not DP. Maybe it can be solved with DP, but yeah, I said without reading it, I will say it's DP, and I start reading it, and it's not DP. Yesterday was DP, and usually they have problem like the knowledge base with the documentation. Right. All right, I am back. Let's continue this journey. So we've done this. Now what we're gonna do is we'll define I and j again. All right. So we define the two, and then what we're gonna do is have a res is 0. Okay. Then what we're gonna do is while I is small equal to k and j is large equal to k. Right? And we say if means I is, what if they're the same? They move together. Smaller means j. Right? If that is the case, then res shall equal to mass dot maximum res means I multiplied by j minus I plus 1. Done. And then we say while I smaller equal to k and means I smaller equal to k. Means I is equal to means I plus 1, I plus plus. Right? We'll move I if we have the same thing. Keep moving until we hit this is equal to the next one. So we'll plus plus. Right? So it's equal to the next one with plus plus, and it's not equal to the next one. Or I is so what happened, I gets out. It is possible I might get out, or if I gets out, then we'll exit no matter what. Else if means j is smaller than means I, so we do the same thing. Res is mass res means j times j minus I plus 1 minus I plus 1, right? And now we say while j is large equal to k and means j is equal to means j minus 1, j minus minus, right? We keep going. Else res equal to max res means I times, this doesn't matter because it's also the same. And then we'll basically do exactly the same thing. Okay, once we're done, we'll return res. Oh, might not be right. Oh. Oh, I guess it just didn't move. So once you're done, you have to move. Huh. I know. I didn't move because it's not the same. So once you're done, you have to move forward. Yeah, I guess that's something wrong. Hold on. So once you do this, you have to move because you use it up, right? You have to move, and then you shall check if it's equal to this. Then you keep moving, keep moving, keep moving. If your current one is equal to the previous one, so you keep moving, right, until it's not equal to the previous one. So yeah, that makes sense. This has to be j minus minus, and then j is equal to +1, right? It's equal to +1, and I keep moving. And if it's the same, then we'll say, oh, if it's the same, that is interesting. If it's the same, right? I and j pointing to exactly the same thing. We just move one side. No, we don't move just one side because they're the same, right? They are the same, and then it's also the smallest, so they already have the maximum possible. So we have to move on both of them, on both. Unfortunately, we have to. And then we'll make this change. This shall be a minus, this shall be plus. Okay, so with this change, let's give it another shot. We can throw in a few more. That should be 0, 1, 2, 4, 5. 0, 1, 2, 3, 4, 5. 0, 0, 1, 2, 3, 4, 5, 6, 7, all the way to 7. 1, 2, 3, 0, 1, 2, 3, 4, 5, 6, 7. Okay, looks cool. Edge case. No, that's actually not quite edge. Let's like do this. Okay, let's give it a shot. Oh, that's pretty good. Got this. $17.93. Build a suffix decreasing array to the left of k and a prefix, not suffix decreasing, suffix min and a prefix min array to the right of k, right? Then use 2 pointers, one at the front and the other at the end of the prefix suffix min array. We start from the overall, right? The overall mean of nums with the longest length, right? That gives us one candidate for a score. Then we must find the next smallest value with the longest possible length. We do that by shrinking, right? By shrinking the prefix suffix min array on the side where a previous min has been taken. The shrinking also skips all the identical, right? All the identical values as the previous min. We stop the shrinking until a different min is found, or we have crossed the threshold of k, right? Keep doing this either on the left or right side until the entire prefix suffix main array has been consumed. Now we have an ON with this. I think this is probably is the solution. Oh, you can do binary search. We must find the maximum score of all subarray that contain this. Yeah, this is already our idea. Now where does binary search come into play? I didn't see the binary search bar. Oh, because this is sorted. Oh, I think they use... Yeah, I don't understand. Binary search. Oh. Set current mean to right. Find I, the insertion. Oh, this is binary search. In left, using binary search, and then you can find the size. Update if. And then what? Iterate J over on the right hand side. At each time we say if that is a minimum, what is, and then we reverse num and do it again. That seems to be not necessary, right? So is this considered monotonic stack? Yes, I think this might be monotonic stack. Not necessarily monotonic stack. If we treat this as a minimum value, we need to know how many elements we can take on the left and right, such that we do not take any elements less than I. How far away the next lesser element is on both sides. If we treat every I as the minimum, how far away the next? Then we can use a monotonic. So it's monotonic increasing. No. On the right is monotonic increasing. I just read the code. We have a left, and we have a stack. From right to left, while stack and nums stack.peak. Now we put the index in it. If this is larger than, so it's a monotonic increasing array for the left. Monotonic increasing, and then we'll go from right to left. Right, we'll go from right to left, and eventually it's going to be an increasing. And left stack.pop. What? What is my method? What is this method? I don't know what this method is. I don't quite understand this monotonic style. Let me read it again. As the minimum element, we need to know how many elements we can take on the left and right, such that we do not have any elements less than this value. So if nums I is on the left hand side, right? So what we want to know is we take this as the minimum. How many we can take, which means we want to know the next biggest, right? Hold on. So I want a monotonic increasing. So if it's a monotonic increasing on the left, so each time we get it, that is going to be the first one, right? We want the first one. First time a smallest value is encountered on the left hand side. The first time it's encountered. So we have to go from right to left, and each time we find something, if it's equal to, then we will pop until we find something that's bigger than me. So if it's smaller or equal to me, right? So we go from right to left, we pick this, and then if it's something is smaller or equal to me, we add it to it. Because what I want to know is, given a value, right? I know it's the first time that I hit this value. It's the first time I hit this value, because that's going to be the smallest, right? It's going to be the smallest. Maybe I need an example to figure out this monotonic array idea. All right, 1, 4, 3, 7, 4, 5. 1, 4, 3, 7, 4, 5. What I want is I have a 1, right? And then I have a 3, and I have a 7. And I know its position is 0. This position is 2. This position is 3. This is on the left hand side. So I know I go from 1, that I need to know On the right hand side, how many is smaller? Not really how many is smaller, if it's also going to be something like this, right? Something like this. In this case, it should be 7 and 4, right? 2, 3, 4. And this is going to be a so it'll be 1, we'll go 4, 3, 3 is smaller, so we'll go 3. And then if it's equal, I just skip, right? Then we have a 7. Or maybe we don't even do 7. Do we do 7? Yeah, we do 7, right? So this is kind of on the left hand side. On the right hand side, I start from 7. So it should be decreasing, right? So 4, 5. 5 is supposed to pop. So yeah, this is increasing. No, this is not increasing. What the hell is this? Ooh. I don't know. I don't know. How far away the next lesser element is on both sides. We're looking for the next smaller elements. We're looking for the next smaller elements. The next smaller element. We'll create an array left, where left I has the index of the first element to the left of I that has a lower value in nums than nums I. That's so complicated. Right I has the index of the first element to the right of I that has a lower value in nums than I. How do we calculate right? Iterating over nums from the left, and then we have a chain of increasing numbers. And the next smaller encounter. We have 6 increasing numbers, and then a 1 that is less than all of them. This 1 at index 6 should be the value of right for all the indices of the increasing numbers. If we maintain a monotonic increasing stack, then this 1 will cause all those numbers to be popped out. So now we know this is the next smallest value to the right for all of them. Okay? So you know who is the next smallest value. Whenever we see an element that is smaller than the top of the stack, it's guaranteed to be the first smaller element for the element at the top. We use the exact same process. We iterate backwards. So we go from right to left. It's also an increasing. So the first time something is small, we pop. Okay, I see what you're doing. So for every one, at every position, you'll know who is the first smallest to your left, or who's the smallest to your right. Then for every position, right? For every position, for an I, okay, for a num's I say this is the smallest value, right? Then I can look to my left to find how far I can stretch to the left, right? And then I go to the right, see how far I can stretch to the right. And then in between, I know everybody is larger or equal to this value, because the first smallest value is going to be here or going to be here. Question, what if this is the smallest? There's nothing smaller to the right, to the left. Yeah, let's say this, we have something down here. Yeah, what's the initial value? So all of these has the smallest here. What is this? What's the first value that's smaller than this lives? -1. It doesn't exist. It's gonna be outside. Okay, it can be outside. That's fine. It can be outside. So if it's outside, let's say this is the range, okay? Then this one is outside and this one's outside. Yeah, let's say we have 0 all the way to n-1, and this is n, this is -1. So what I do is this minus this, -1. Yeah, -1. So the stack method is, okay, and then something bigger. Yeah, we have something bigger comes in. And who is the first one to the right of it that's smaller than this? Yeah, actually, if this is the smallest value, then to the left I have one. To the right, to the right, so if you're on the left hand side, you always look to the left. If you're on the left hand side, you always look to the left. And how about on the right hand side? So I think it should be restricted only to the left, right? Yeah. When we go this left, we shall not go beyond. So the left will only be here, and the right so you have to cover K. Should be the first smallest, then this on the right hand side, right? On the right hand side. So Yes, this is what I thought. Thus, we can only use an index I as the minimum if left I is smaller than k and right I is larger than k. Otherwise, we don't use it? You just throw it away? Really? You can do that? If I say left exists, but right all does not exist, so you are the smallest one, and the right does not exist. Now that right exists. It's just the right exists. It's just the smallest is here. So if you are the smallest, then cross. Oh yeah, it makes sense. Across k, you cannot make you the smallest. That makes sense. Yes. Okay, I agree. This is a method. I don't think it's as easy as mine. I still think my method is better. Yeah, I think my method is better. Let's put it out. I think this method is better. Okay, they also have a greedy. Yeah, we should move in the direction of adding greater elements. That's true. Yes. Oh, and just like at each step, you're trying to make sure you can add more, right? Mm-hmm. Yes, because this is larger. Yes, yes. Oh, greedy is brilliant. Okay, so I think we can do. Let's try both. Okay, so this is the monotonic stack approach from the second solution of the official solution. The ideal is that we go through nums one by one and designate each nums I as the current smallest value of the potential good array. Now the question is to find out what is what is the longest version of such good array. And this problem can be written in another way, right? In another way, as to find the first value smaller than nums I on the left, and the first value smaller than nums I on the right, right? Then the subarray in between is a good array with nums I as its min, and we will have the length of the good array as well. To find the first value smaller than nums I on the left and right, we can use a monotonic stack, right? Suppose we are doing a monotonic increasing stack, right? And the first time a smaller value is encountered, all the bigger ones currently in the stack must be popped. As they are popped, they can record the smaller value as the first value smaller than itself on the right. Okay, so for this, we'll have in left nums.length. Okay, then we can say left I is the index of the first value smaller equal to, right? Smaller equal to, I have that. Smaller equal to nums I on the left, right? Then we can do it exactly the same. We can say right I is the index of the first value smaller equal to on the right. Okay, then we need a monotonic increasing stack. We can say stack integer mon new stack. Okay, then we'll do for int I equal to 0, I smaller than nums the length I plus plus. We push it into, right? We can say while mon dot is empty if it is not empty, and mon dot a peak, right? This is the top of the stack, right? Now peak is the index, right? And we'll push the index in. So we have to say nums this, okay? If it is, what if it's equal? I don't do it. Left array dot fill, arrays dot fill left should be filled by -1. Arrays dot fill right, on the right should fill nums dot length, right? So if this value is larger than nums I, right, then mon dot pop. Okay, but we shall say write this equal to I is the first value, num's I is first value smaller than mon.peak, num's mon.peak. So we record it, right? So we record it. Actually, when we record this right here, right here. Pop. Once we're done, mon.push I. So that's that. Okay, once we're done, mon.clear, and then for int j equals to nums.length -1, j large equal to 0, j minus. Same thing, while not mon.dot is empty, and nums mon.peak is larger than nums j, right? Because we go right to left, the same, increasing with the first one that's larger than, then we say left mon.pop shall equal to, this is the first one on the left hand side, right? Equal to I, j. And then we say mon.push j. Okay, done. Now we're gonna serve for int I equal to 0, I smaller than nums.length, I plus, of course int res equal to 0. Now for each one we can say nums I is the smallest, right? But first of all, it has to be the smallest, must be larger than k, right? It cannot even be equal to k, because if it's equal to k, then because the subarray is within the 2, so if left I is smaller than k and right I is larger than k, okay, then res equal to math.maximum res nums I times right I minus left I minus 1. So we go through all this and return res. Yeah, it's slow because we have a stack, right? So that's that. That's method, yet another method. Owen as well. Yeah, I like my method. Definitely like my method. It's a prefix. Maybe we can post it, but I'm pretty sure people have found the method as well. But I can just post it, it's fine. All right, the last one. All right, this is a third. Okay, greedy. This is third solution method from the official solution, and its idea is to start from nums k, going either left or right, and each time we include the larger one, because by doing so we are increasing the chance of including of extending, of increasing, of elongating the subarray while not decreasing the minimum value, right? The minimum value too much. Now the official solution has a proof for that. Simply put, if we choose not to go with the larger value, right? If we choose not to go with a larger value, then we have to go with the smaller value. In that case, going with the larger value in the next round will not affect the overall min, yet we can extend the length even further, right? Thus, going with the larger value is always the optimal choice, right? This is O(n) as well. I feel this one is the easiest implementation wise as well. And we can just say res equal to nums k, right? And then we'll have 2 int I equals k minus 1, int j equal to k plus 1, right? Say while I is larger equal to 0, or j is smaller than nums dot length, int, yeah. No, I think both should start with k. No, we should do that. Then what? If both within, right? Now we might as well just while true. And then we can say if I is larger equal to 0 and j is smaller than nums dot length. That's the case, then we pick the bigger one. If nums I is larger equal to, yeah, that's fine. Doesn't matter which one we pick if it's equal. Nums j, right? Then, oh, we need a current minimum. Int current min equals nums k, right? Then what do we say? If this is larger than this, then we pick the larger one, and then we say current min shall equal to math.min current min and nums I. Res shall equal to math.maximum res current min times so I pick I, right? I have picked I. We have not picked j. Let me I minus minus first. Then we can say j minus I minus 1, because I picked I and I minus minus, so it's outside. J I didn't pick, so both are outside, so this one will be right. So I do that. Else I'll do current min equal to math.min current min nums j, right? And then j plus plus, yeah, I can put them in one line, right? J plus plus, and then res equal to math.max res current min times j minus I minus 1. Okay, so that's if both, right? That's if both common part can be extended. Nah, I don't want to. So anyway, so this will be if both are good. Else if I is larger equal to 0, so j is already to the end, then we have to do this, right? Then we have to do this. Else if j is smaller than nums dot length, then we have to do this. Right? And else break. And now I'll return res. Okay, here's my final implementation. Still not as fast as mine. Alright, I think this solution has a better implementation. I feel it does. Oh, it has this and this. Yeah, I actually like this one better. So we check it first, right? If it's larger than 0, then but anyway, that's how I do it. Yeah, it's fine. I'll just do it this way. It is annoying, right? Yeah, it is annoying. I larger equal to 0. J smaller than nums dot length. Okay, so so I need to find if I larger equal to 0, nums I, right? Nums I, otherwise 0. Yeah, if this is smaller than, or we can say if it's larger equal to j smaller than nums dot length, nums j 0. Yeah, let's put more parentheses to make sure there is no ambiguity. Okay, right. If this is the case, right, I larger than 0 is this. Otherwise, we do this. J, do this, I do this. Once this is the case, we'll do this. Else, I mean, in this case, yeah, this is the same thing. We don't have to do it every single time. All right, this is the same thing. Come on. Oh, for the setup, nah, screw it. We'll do it here. Else, we'll have to do this, right? And once we're done, we will do res. Do we have this one? Yep, this is the better one. Okay, now we're good. Now we're good for today. Many methods. All right, that will be it. I will end right here and see you guys tomorrow. Adios.